Yesterday we looked at an analysis of a cathode ray tube that J.J. Thomson used in 1897 to eventually discover the electron. This cathode ray tube consists of this evacuated tube. All the air is sucked out of this tube, so you don't need to worry about these mysterious cathode rays getting bothered by any air or anything else inside there. It also consists of a couple electrodes. This electrode, the negative terminal, it's a little bit confusing if you take chemistry, but this negative terminal would be called the cathode. Over here we'd have a positive terminal that we call the anode. And we put a little hole in that anode so that whatever comes out of the cathode can make it right through the anode. Hook it up to a power supply down here. This is a bit of a simplification because this power supply would have to be some kind of large potential difference in order to cause the electrons, as we turns out these things are electrons, right? As it causes these electrons to jump the gap, we'd have to have a big potential difference. Remember, in 1897, this mysterious something was leaving the cathode, going to the anode, going through, and then striking the screen. We could see where they strike the screen because we got this screen painted with this phosphorescent coating, and it glows whenever something like this cathode ray or this beam of electrons strikes it. Thomson wanted to find out what makes up these mysterious cathode rays. So he introduced a magnetic field here. What did he find happened when he introduced a magnetic field there? These cathode rays did what, Ethan? Yeah, they're going to be deflected downwards. So they're going to go in a circular path downwards. And what did that tell them? Remember, in 1897, we knew lots about charge and lots about magnetic field. We just didn't know about electrons, right? What did that tell them, Emma? Yeah, they're negatively charged. So we don't have negatively charged subatomic particles. We don't have electrons yet, but we have negatively charged particles. So it's at least these mysterious unknown cathode rays are particles, negatively charged particles. He did an analysis with this, and that analysis was an analysis that we've done many times before. Fc is equal to Fm, or mv squared over r equals qvb. Cancel out the v's. Yet mv over r equals qb. He's got a problem now, though. Of these 5 variables left, he only knows what 2 of them are. He can measure r by where the mysterious beam of negatively charged particles strikes the screen. He can measure b because, well, he introduced the magnetic field, so he's got to know what the value of b is. Still doesn't know what m is, doesn't know what v is, doesn't know what q is. So what does he do next? What does he do next? No one? Yeah, he puts in parallel plates over here. This plate would be positive, and this plate would be negative. And he also, at the same time, introduces in the same place, another magnetic field. That magnetic field, if we think about the hand rule for deflection, thumb, fingers, palm, the magnetic force would end up being downwards, but the electric force on these charged particles would be upwards toward the positive plate. If the speed is too big, then the downward force is greater than the upward force and the particles get deflected downwards. If the speed is too small, then the upward force is bigger and the particles get deflected upwards. If the forces are the same, if they balance, then the particles are going to go straight through undeflected. Those are the particles that we care about, the ones that go straight through there and enter this, what we call the main chamber right here, straight on. So we're going to say for that velocity selection chamber, as I named it yesterday, Fe equals Fm for the particles that we care about. QE equals QVB. Q's cancel. V is equal to E over B. So now we've got the speed of the particles that go straight through, which those are the ones that enter the main chamber. So I can plug that value of speed into there. Now the only thing I don't know is Q and M. Rearrange this to solve for the charge to mass ratio. And it becomes V over B times R. Okay, that number was, you don't need to remember the exact number, 1.76. You don't need to remember the exact number. That number was big, right? Big. It's a big number. And what does that tell us about the mass? If this is big, then the mass has got to be small. In fact, if this is bigger than anything ever measured, then this has got to be smaller than any mass ever measured. Therefore, these negatively charged particles we now consider to be negatively charged subatomic particles. If it's smaller than the mass of an atom, then it's got to be subatomic. It's got to be smaller than an atom. Now there is one more thing over here we can do. Call this the acceleration chamber. In the acceleration chamber, we occasionally have to analyze that. And when we do, what do we do to it? Charged particles accelerating, cars going down a hill. Yep. Ethan? Yeah, EI equals EF. And we start with potential energy at the beginning, and we end up with kinetic energy when the electrons reach the anode. Right? So prior to 1897, people had seen these. Called them cathode rays because we didn't really know what they were. They just came from this cathode. But post 1897, we discovered that, or Thomson at least discovered that they're negatively charged subatomic particles that we call electrons. Which, by the way, leads us to a model of the atom. Some people call it the plum pudding model, the raisin bun model, the cookie dough model, chocolate chip cookie dough model. The atom is a sea of positive charge with a bunch of little electrons floating around inside it. Ollie, question? Didn't know the charge of an electron. Thomson didn't use this formula. QV is equal to 1/2 mv squared. Thomson didn't use this formula. Thomson found speed by doing this, and Q's canceled out of there, right? And then plugged it back into here. He still didn't know what Q or M was, so he solved for the charge to mass ratio. So Thomson couldn't do this because he didn't know what Q was. It wouldn't have been great anyways, because in the end, the speed that you calculate there is actually the maximum possible speed, not the exact speed, but the maximum possible speed. So even if you happen to know what Q and M was, which he didn't, it wouldn't have been the best way to do it anyways. So would you say, like, if you're doing any questions where you're trying to speed? Yep. If it goes over what he discovered, then you're most likely wrong. That's the maximum. Well, no, I wouldn't say that. No, no, because it depends on the potential difference. Okay, if you're given a problem and you're given information about the velocity selection chamber, use it to find the speed. If you're not, but you're given information about this, well, then use this to find the speed. It's just not the best way to find speed, that's all. Eve? Okay. Yep. Yeah, absolutely. Absolutely. That's a great question. Could we be given variations where the parallel plates are reversed? If the parallel plates were reversed, negative on the top, positive on the bottom, then the magnetic field would also have to be reversed, though. Otherwise, you couldn't get them to balance because both forces would be in the same direction there. I've seen a question once, actually, talking about variations, where you had something like this. Here's the cathode, here's the anode. You don't have any three separate chambers. You just have this and this. Well, that's going to go straight through every time, right? Unless you remove the electric field, unless you turn off the power to these particles, right? To these plates, right? So maybe what you do is find the speed of the particles that are going straight through there. Find the speed of those particles by using E over B, right, the velocity selection chamber, and then instead of going to the main chamber, the velocity selection chamber turns into the main chamber, where you remove the electric field. We treat it the same way. This would be chamber 2 right now, but if we remove the plates, it would become chamber 3, right? Again, variations, but we treat them mathematically the same way. Okay. All right, we had 3 questions for homework last night. Let's take a look at those. I know we want to go over something here. Does anybody have specifics here? No? 2? 3? Okay, let's take a look at 2 and 3 here. 2 is a true cathode ray tube because it's using an electron. Question 3 is using a carbon-12 ion, so that would be a mass spectrometer, but we analyze them in the same way. The speed of an electron moving in an arc of radius 0.1, we're going to say this is the main chamber, where we say Fc is equal to Fm. Main chamber because we've got just a magnetic field and it's going in a circle. If it was going in a straight line and it was a magnetic and electric field, then it would be the velocity selection chamber. So we're going to say mv squared over r equals qvb. We're solving for a speed here. One of those v's cancels. Now, in order to do this, you have to know the charge and the mass of the electron. Okay, this is not a Thomson experiment. He didn't know what they were. We do know what they are. Okay, we can find that speed. Remember, Thomson would have known what the speed was from the velocity selection chamber and then found the ratio of charge to mass. So if we're finding the speed, we have to know what Q and M are. Charge is 1.6 times 10 to the minus 19, even though it's not given to us in the question. It's on our data sheet. B is 1 times 10 to the minus 4. R is 0.1. And M is 9.11 times 10 to the minus 31, also on our data sheet. What do we get for speed there? I don't know, but I'm going to guess 10 to the 5, 10 to the 6 meters per second, because that's usually what we end up getting. 1.8 times 10 to the 6 meters per second. Okay, if I got an answer that was 10 to the 7 or 10 to the 4, it doesn't mean I'm wrong, but I would probably go back and check my work, because usually 10 to the 5, 10 to the 6. All right. Number 3, I should say, says a carbon-12 ion has a charge to mass ratio of 8.04 times 10 to the 6. What's the radius of the ion's path when it travels 150 kilometers per second? Not kilometers per hour, kilometers per second to a magnetic field. Once again, this would be the main chamber because there's just a magnetic field and it's going in a circle. So we'll say Fc equals Fm, or mv squared over r equals qvb. Now we're looking for radius here. If you solve for radius, take the r off the qb down, I get mv over qb. I don't like doing that actually for this question. Why not? Yeah, the givens that I have given to me, v, b, and q over m. What do I need in order to solve it this way? Not q over m, m over q. Now you got a couple of options here. Okay, option number 1, with the way that I have this written down right now, if we know q over m, then m over q would be what? The inverse of that, 1 over 8.04 times 10 to the 6. We could do that. Yeah, that's fine. That's not the way that I would prefer to do it, though, myself personally. I would rather say, let's solve for q over m. Let's solve for q over m, and then just sub the number for q over m in like this, and then rearrange it. 8.04 times 10 to the 6 equals v over 0.5 times 150,000. Okay, it's no better, but for me it seems just a tiny bit easier. Okay, whatever works for you, though. Okay, so what I'm going to do here now is take that 8.04 times 10 to the 6 and times it by both things on the bottom there. Oh, well, that's not right then. We're looking for r? Yeah, I guess so. Calculate the radius. So we still have 8.04 times 10 to the 6 equals 150,000. Thank you for publicly embarrassing me on my recording here now. Thank you. B, 0.50 Tesla times the radius here. I'm going to take the radius up. It becomes R is equal to 150,000 divided by 0.5 times 8.04. So you see what we're doing here. Right? We're essentially taking 1 over 8.04, right? Which is what Ethan, I think, told me to do in the first place. Let's calculate this. 150,000 divided by, use some brackets on the bottom, 0.5 times 8.04 times 10 to the 6 gives me 0.037, 3.7 centimeters. Is that our answer? Yep. Good. I do want to do a couple multiple choice questions today, starting with question 146. Here's a cathode ray tube. We talked about variations. Julia was asking about variations. Here's a variation, right? We have deflection coils here, which provide the magnetic field. A vacuum here. It doesn't look like we have a magnetic field in there anywhere. That's okay. Okay, we still have an acceleration chamber. which is what we really need to deal with here. The electron hits the screen at a speed of, well, we're going to say EI equals EF here because it looks like all we have is information about the acceleration chamber. QV equals 1/2 mv squared. Now, understand that when we solve for that VF, it's not the actual speed necessarily, it's the maximum possible speed, but it's the best we can do here. When we solve for that, 1.6 times 10 to the minus 19, V is 2500, 9.11, VF, I believe, does work out to be 3.0 times 10 to the 7. Is that right? Yes? How many people got that? All right, I want to take a look at two more questions that go with this information here on this one. The questions that I want you to do are page 148 and 149. This deals with some stuff that we've never heard of before. We will deal with it soon, but in the end, what have I told you about it? Hey, if you're talking about radioactivity and we haven't done radioactivity yet, how relevant is it? It isn't, right? It isn't relevant to the question here. So I'm going to, just so that you can have things on the same page here, there's your information. We're looking for, in question number 146, the speed of the undeflected beam. So we're looking for the speed in there or the velocity in there. And we're also looking for, using the charge to mass ratio, what kind of particle it is. All right, give that a whirl here. You can refer to it in your worksheet booklet, or you can just refer to what's up on the screen now. So the first question, I wanted us to find the speed. What are we dealing with here? This isn't really a cathode ray tube, right? Because we've got radioactive isotopes that aren't electrons. But in the end, we can treat it like that. Okay, these particles are going through an electric field and a magnetic field. That's like the velocity selection chamber of a cathode ray tube. So let's analyze it like the velocity selection chamber of a cathode ray tube, where, because they're going through undeflected, Fe will be equal to Fm. Q times E is equal to QVB. Q's cancel, so we don't need to know what the charge is. V is equal to E over B. All we're going to do here is say the electric field, which is, what is the electric field? Oh, we don't know the electric field. Interesting. How do we find it? How do we find the electric field? Maddie, how do you find the electric field? Looked like you were about to raise your hand, and then I realized you weren't, but that's okay. I'm going to call on you anyways. Good. Excellent. We're going to say E is equal to delta V over delta D. Electric field, not energy, is delta V over delta D. So let's get this and this to get electric field, and then let's divide it by the magnetic field of 0.70. When we do that, we're going to get, I'm going to say something times 10 to the 6, times 10 to the 5, 10 to the 6. What was the answer there? Who's got it? 2.5 times 10 to the 6 meters per second, which we're going to record as 256, right? Okay. And finally, using the charge to mass ratio of the particles, the scientists determine the particles to be what? Well, let's find the charge to mass ratio first. Oh, look. Again, we talk about variations. Julia, when the electric field is eliminated, that's one of the ones that I was talking about before, right? Then we have just a magnetic field. When we have just a magnetic field, it's like the main chamber, where we can say Fc equals Fm. We say mv squared over r equals qvb. And we say q over m is equal to v over br. So you know what the speed is, you know what b is, you know what r is. Get the charge to mass ratio. Who's got that? 4807. Okay, that's close enough there. So we're going to say, what is that, 4.81 times 10 to the 1, 2, 3, 4, 5, 6, 7. 4.81 times 10 to the 7. I'll tell you right now, that's not the charge to mass ratio of an electron, because I remember what that is, right? It's 10 to the 11. So you want to find out what it is? Well, I know it's not C, because charge to mass ratio of an electron is times 10 to the 11. I know it's not B, because the charge to mass ratio of a neutron is 0. 0 coulombs over the mass is 0. Of a proton, well, let's just calculate the charge to mass ratio. 1.6 times 10 to the minus 19 over the mass of a proton Okay, I don't know what that gives me. Alpha particles, the charge is 3.2 times 10 to the minus 19 over the mass of the alpha particle. Which one was it? Which one did it match up with? Okay, in the end, this number here that Adele gave us, 4.81 times 10 to the 7, should match up with one of these. Does it? What's the number here? Okay. Okay. If it's the same to the rounded number, then that's what we want there. 10 to the 6 or 10 to the 7? 10 to the 7? Okay. So we found the charge to mass ratio using, well, basically a cathode ray tube or a mass spectrometer, okay, V over BR. And then we found the charge to mass ratio of each of these things by just simply dividing Q by M, charge by mass, and it matches up for an alpha particle, so it must be alpha particles. All right.